Hello and welcome to this video dedicated to acid-base and functional group exchange reactions. The aim of the video is to give you an overview of typical reactions which involve functional group exchanges. I will be dividing the video in 4 different segments. In the first part, I will talk about acid-base reactions. In the second part, I will talk about nucleophilic substitutions 1 and 2. In the third part of the video, I will talk about elimination reactions. And finally, in the last part, I will tackle addition reactions, including addition to conjugated carbonyl groups, specifically Michael addition and the Robinson annulation. The content for these videos is based on chapter 2 in Smith's organic synthesis, and you have a copy of this chapter available through the Novel database in the Blackboard for the module. Additionally, the Michael addition and the Robinson annulation are based partially on some sections of chapter 9, and again you have a link to that chapter, to that section of the chapter 9 in the module Blackboard. So many chemical reactions involve incorporating or changing a functional group in a given compound to achieve our target molecule, the compound of interest. Sometimes we introduce those functional groups because they're a structural feature of the final target. We want them in the final compound. And sometimes we need them in the structure of the intermediate compounds during the synthesis because we need to manipulate those functional groups to alter them in some way to form the desired structure, the desired compound. For example, we've got here how could we synthesize this compound in which you have a bromine atom and a hydroxyl atom, a hydroxyl group in 2 adjacent carbons, starting from cyclohexanone? Well, a typical way of introducing 2 groups into adjacent carbons is a substitution in an alkene group. So a first step would be to convert your cyclohexanone into a double bond, into an alkene group, and you can do that by first reducing the carbonyl group to a hydroxyl, and then it's not easy to do an elimination reaction that produces a double bond with the hydroxyl. It's much easier if you have a halogenated compound. So the next step is to prepare a brominated compound from the alcohol formed from the reduction. And then using a strong base, potassium hydroxide, for example, you can form the double bond. And then is when you can add, using bromine and water, for example, when you can add the 2 functional groups you're interested in, the hydroxyl group and the bromine atom. So this, for example, is a nice example of how you can play with the presence of functional groups and how you can manipulate those functional groups to obtain your desired molecule, your molecule of interest. So this is just a table classified with some general classification of how you can divide functional group exchange reactions. You can have acid-base reactions, you can have substitution reactions, and elimination reactions to form, for example, double bonds or triple bonds. You can have addition reactions, and those are in a double bond or a triple bond. You can also have nucleophilic substitutions, for example, nucleophilic acyl additions on a carbonyl group. And finally, you can have oxidation and reduction reactions. This is an example of how a nucleophilic aliphatic substitution looks like, and how you have a starting compound in which you have a leaving group, X, could be, for example, a halogen or an acetate group or a sulfonic group, and then you add a nucleophile, and this is an example of some nucleophiles you might want to include in your target compound. Another example of a reaction in which you change functional groups, is a nucleophilic acyl substitution. You start, for example, from a carbonyl group, and adding a nucleophile, you obtain the alcohol and the nucleophile incorporated on your structure. Another type of reaction you can have is an elimination reaction, in which you start from a compound in which you have a a living group, a potentially good living group, let's say, for example, a halogen, and then you form the double bond by eliminating those two atoms. Acid-base reactions are widely spread in synthetic organic chemistry. They are integral to many reactions. They are not only associated with one type of reactions. Many reagents, for example, that add to a carbon-carbon double bond are acids. Think, for example, of hydrochloric acid. And the reaction is an acid-base reaction. The alkene reacts as a base, donates electrons to the acid. And you can, this is just a way of, in this slide, you can have a way of generalizing those addition reactions to a double bond or to a triple bond. So for example, starting from a double bond, you can generate a single bond and the addition of two different atoms to your double bond. Or if you start with a triple bond, then the addition would produce the corresponding double bond, the corresponding alkene from an alkyne. Many organic molecules react in a way that can be described as a Bronsted-Lowry acid-base reaction. Carboxylic acid, phenols, or 1,3-dicarbonyl compounds of this structure are acids. Weak acids, typically much weaker than common mineral acids, like for example hydrochloric acid. Many organic compounds, for example amines and phosphines, are bases, and again generally weaker than typical bases like sodium hydroxide or potassium hydroxide. And then you have compounds that can easily behave as amphoteric, and those, for example, could be alcohols, in which they will behave as an acid or a base depending on the context of what they are reacting to. So for example, in this example, the hydroxyl group is able of getting protonated and reacting with the protons from the hydrochloric acid in an acid-base reaction, and it behaves as a base, forming this protonated water that then can be easily eliminated by the chlorine group to form the halogen compound, the chlorinated compound. Ethers are also weak bases, and amines, as I said before, are weak bases except when there are presence of a very strong base, in which case they behave as they are forced to behave as acids. And the example is in Grignard reagents and organolithium reagents, in which they behave as acids. Other atoms or structures that can behave as acids or bases are, for example, the alpha carbon of a ketone. The alpha carbon of a ketone is a weak acid. So you can have an acid-base reaction with a base. So for example, in this example, it is reacting with the sodium methoxide, and you can form the enolate anion by just bouncing the double bond to a negative charge over the oxygen. So this would be the acid, and this would be the conjugated base for the butanone. And in this case, this would be the base, and this would be the conjugated acid for the sodium methoxide. So the conjugated acid for the sodium methoxide would be the ethanol. And ethanol is stronger as an acid than butanone. So the equilibrium of this reaction is strongly displaced towards the left, towards the reformation of the reagents from the product. And that is because the ethanol is a stronger acid than the butanone, so the reaction is more favorable, shifting the equilibrium towards the left. Acid-base reactions are equilibrium reactions, and the position of the equilibrium is determined by the acidity constant. And the acidity constant is determined by the interaction of the acid-base pair and the corresponding conjugated acid-base pair, and how stable the products they are with respect to the reagent. So when you have something in the structure of your product that stabilizes that product, that shifts the equilibrium towards the formation of the product. So for example, if you compare the acid properties of phenol and 4-nitrophenol, 4-nitrophenol is a stronger acid than phenol. They are both weak. As you can see, the pKa's are both quite large, but within both, 4-nitrophenol is a stronger acid. And why? Because when phenol reacts with a base, it is possible to form resonant forms. But when nitrophenol with 4-nitrophenol reacts with a base, then you have additional resonant forms, because the nitro group also participates on those structures. So then the nitro group helps stabilize the product and shifts the reaction towards the formation of that product. Basicity in organic molecules as acidity is determined by the type of substituents of your carbon skeleton. So you can have electron donating groups by inductive effects through the sigma bond, or electron withdrawing groups, again through inductive effects through the sigma bonds. And then you have electron donating and electron withdrawing groups, but due to resonance, to the formation of resonant forms. So for example, here we've got two derivatives of aniline. One is methylaniline and the other one nitroaniline. And of those, the most basic one is the methylaniline. And the reason is that the methyl group donates charge to the ring through a resonant effect. So it is an electron donating group, while the nitro group is an electron withdrawing group. So withdrawing charge from the benzene ring means that the benzene ring withdraws charge from the nitrogen of the amino group, and that means it makes it less reactive, it makes it less basic. While in this case, in the methylaniline, the electron flow is in that direction. The methyl group is communicating a small but some electronic charge to the ring, which then can donate that electronic charge to the nitrogen of the amino group, which makes it more basic. Why do we care about acidity and basicity? Well, for example, if you have if you have a very strong Lewis acid in your reaction, it could degrade both the products of the starting materials, and that could be a problem, attacking the reagents or the product's form. You can also have, if you have very strong Lewis acid, for example, aluminum chloride is very reactive, and that means that as a catalyst is very unselective. It will react with almost any Lewis base that you can think of. While zinc chloride is a less strong as Lewis acid, so then it can selectively react it can selectively participate in reactions where you have halides and alcohols and also olefinic carbons, rather than react indiscriminately with all the functional groups present in the molecule. So this is the end of this part of the video on acid-base chemistry. Thank you very much for watching, and I hope this was useful.